Today we're going to talk a little bit about similarity in objects. Now, two objects are similar if they have the same shape, but they can be different sizes. And by same shape means all their corresponding angle measures are going to be congruent. However, the lengths of sides are going to be all at a specific scale. So for my big star here, if the original star is the larger one, a similar image to that would be the smaller one here. If I label the first image A, the smaller image is going to be A prime. So we call the smaller image the A prime. This is actually the image, just to get the terminology here, and the original is called the pre-image. And similar shapes have a scale factor. So to obtain that scale factor, I could measure a length of the image, and let's just call that length 3 for now, and measure the length of the corresponding side on the pre-image, and let's say that's going to be 8. Well, if I look at the order, I'm starting with the big star and I'm ending with the small star, so the scale factor is going to be, sometimes the scale factor is denoted R, and sometimes it is denoted by a K. But the scale factor here would be 3 over 8 because I'm shrinking the image, or I'm shrinking the pre-image down to find the image of A prime. Now, we can also find the center of dilation. And the center of dilation is found by connecting corresponding points. And if you do that to two of them, they're going to intersect at the center of dilation. So we've done some constructions a long time ago where we've used the center of dilation and actually measurements to create an image from its pre-image. We can find the scale factor again between corresponding parts, or you could actually measure along the line. This would be the original measurement, and this would be the new, and that would still have a ratio of 3 over 8 when you reduced it down. Next, we're going to briefly look at what happens when you dilate a line or a ray or a line segment. So here we have, we'll consider this a line, and I have 2 points on it, A and B, and my center of dilation is O. And let's say I'm going to dilate around from O with a scale factor of 2, and I want to dilate this line AB, or we'll consider it a line segment AB. To do that, I would construct it, and, oh, that's not a very straight line. I would have to extend my dilation lines out, and whatever this distance is, since I have a scale factor of 2, I would have to double it here. So a very, very rough sketch of this. My new A prime would be there, and what you would find is I would measure this length, and I would come out here. You would find that when you dilate a line or a ray or a line segment, the image is going to be parallel to the original. So when you dilate a line, you get a line. When you dilate a ray, you get a ray. When you dilate a line segment, you get a line segment. And if the center of dilation is not on the line itself, then you obtain a line parallel to the original. The distance between A prime, B prime is going to be double the distance between AB. So A prime, B prime is going to be twice the distance of AB. And everything is going to have the same proportion. Now we can also talk about similarity transformations. These are used to describe the set of rigid motions and dilations to map one image to another. So if you look at the two circles here, one thing you have to remember is that all circles are similar, all of them. All circles are similar. So I can always map one circle to another. In this case, I'm going to start with my circle O. It has a radius of 9, and I want to map it to this circle with a radius of 5. Now the orientation of the radius is irrelevant because that's just a measurement. What we do need to do is we need to translate O, and let's call the second circle A, translate O to A with that vector. So if I'm going to describe the transformations, it's going to be a translation of OA, of circle O. Once it's translated, I need to scale it down so it matches the radius of circle A. To do that, I need a dilation. I'm going to dilate, and since I'm making the circle smaller, my scale factor is going to be 5/9. It's always the ratio of the radii. So my second transformation, I'm going to dilate about A, because now they're both on A, with a scale factor of 5/9, and that's going to be circle O. That's how you would describe a similarity transformation to map circle O to circle A. The key is the scale factor. If I'm shrinking the circle, then the numerator is smaller than the denominator. If I were mapping A to O, then my scale factor would be flipped. It would be 9/5. Two triangles are going to be similar if their corresponding angles are congruent. That's the only thing that we need to show that triangles are similar. So if I take a look at these two triangles here, and if I'm going to be given that, let's say angle A is congruent to angle D, and angle B is congruent to angle E. Well, we know the sum of the angles I'll have to add to 180, right? And same thing over here. In any triangle, the angles add to 180. Well, if these two are the same, and these two are the same, it follows that the third angles are also the same. So the minimum requirement to prove triangles similar is not angle, angle, angle. In fact, all we need are two pairs of corresponding angles to prove them similar. And that's angle, angle, similarity. So that's all I need if I'm going to prove triangles similar. Once I know that, if I know that triangles are similar, then corresponding sides are going to be in proportion, which means AB over DE is equal to AC over DF, which is equal to BC over EF. The final thing we can discuss is the ratio of perimeters and areas with similar objects, because there is a relationship. If I have two similar triangles, I have ABC and DEF, and corresponding sides are 5 and 10, and I say that ABC is similar to DEF, then my scale factor is going to be 10/5. So we're going to call it a scale factor of 2. We're starting with A, and we are increasing it. So my scale factor is 2. Well, what that means is there is a linear relationship between the scale factor and the perimeter. So let's say the perimeter of ABC is 19. Then the perimeter of DEF is going to be double that because of my scale factor of 2. It's going to be 2 times 19, and that gives you 38. Now there's a different relationship with the areas though, but there still is a connection. Let's say the area of triangle ABC is 15. Well, the area of DEF is going to be equal to 15 times the scale factor squared. That's the relationship, because think about your area formulas. We are usually multiplying, we're always multiplying two dimensions together. and your units are squared. So we are squaring the scale factor to get to the new area. This ends up being 15 times 4, so that is 60. So between perimeters, if you have similar triangles, then the perimeters to get from one to the other is just multiplying by the scale factor. That's a linear relationship. For areas, you have to square the scale factor to get to the new area. And then eventually with volumes, there's another relationship where you are cubing the scale factor, but we will cover that in a few days.